is the derivative function. So the derivative at a point. In chapter 1, we explored limits and we touched base on this formula right here. This formula has two interpretations, okay? The first one is the slope of the tangent to the graph y equals f of x at this point here. Okay, and number two, the instantaneous rate of change. Okay, so we're talking about slope, we're talking about instantaneous rate of change. Okay, of y equals f at x with respect to x at x equals a. Now, here's a concise notation. This is the derivative of f at the number a. Okay, same thing here. We have the same formula. This is something new. So this notation means the derivative. This accent or apostrophe here, this we call prime. So this is like f prime at a. Okay, and since we're dealing with limits, this only occurs provided the limit exists. So example 1, let's just recap from what we did in the last section. Let's find the derivative of f at x equals x squared at x equals -3. Okay, so generally we go limit as h approaches 0. We have x plus h squared minus x squared all over h. Okay, and now let's actually just sub in the number 3. Sorry, -3. -3 plus h squared minus -3 squared all over h. So now let's just expand. We get 9 minus 6h plus h squared minus 9 all over h. These 9's can cancel out. Then I'm going to factor out an h. So in this step, again, I'm going to factor out an h. -6 plus h is what we're left with after we cancel out the h's. Now, this should be f prime at -3 because in this step we actually subbed in the -3. Okay, now let's sub in the 0. I get -6. Okay, so therefore f prime at -3 equals -6. So the slope or the instantaneous rate of change when the function is at -3 is -6. Now we're going to take a look at how to do this for more than one outcome. So just a general form. So an alternative way of writing the derivative of f at the number a is f prime at a equals, and then here it is. Okay, the limit as x approaches a of f at x minus f at a all over x minus a. And what we're going to do is we're going to use this general form when we're repeating the process because it becomes a little bit tedious. Okay, example 2 here asks us to find the derivative at -2, 0, and 1. Well, we can go down the entire page and we can do this 3 times, or we can simply do it once with the general form and then just sub in those values. So let's do the general form. The limit as h approaches 0, we can do the exact same thing. We're dealing with x squared. So x plus h squared minus x squared all over h. And we saw this in on the last screen or in the last example. But what we're going to do now is instead of subbing in the -3, we're actually just going to expand using these numbers and these letters. Okay, x squareds go away. We are left with 2xh over h. H's cancel. We're left with 2x. We don't even have to sub in the h approaches 0 or h equals 0 because there's no h's left in the equation. So the general form for the equation of x squared is 2x. Now, let's find the slope at -2. Well, all we do is take that general form and we find that it's -4. Let's find the slope at 0. Take the general form, the slope is 0. Let's find the slope at the point 1. Sub in the 1. Okay, the instantaneous rate of change at 1 is 2. So we can use this general form very quickly. Okay, so let's actually investigate x cubed, x4, and we probably won't get around to doing x5, but you can do that independently. Okay, so if we have f prime at x equals the limit as h approaches 0, okay, we have x plus h squared, or cubed, minus x cubed. Okay, let's actually expand x plus h cubed. Okay, thinking back to grade 11, I'm not going to do this by foiling. I'm going to do this by binomial expansion. So we have x cubed plus, I'm going to do Pascal's triangle, just very small down in this corner. Okay, we're dealing with 1, 3, 3, 1 as the coefficients. So 1, 3, x squared and h, 3xh squared, and 1, which is h cubed. And that's all going to be over h. Oh, and we have minus x cubed, sorry, from the original. Okay, those two cancel out. Now in the next line, I'm going to factor out an h from what's left. So we have 3x squared plus 3xh plus h squared all over h. Those cancel out. Let's sub in 0. When we sub in 0, we realize that this term here goes to 0 and this term here goes to 0 because both of them have h's in them. So we're left with 3x squared. Okay, and finally, let's do x to the 4. Okay, so we got x plus h to the exponent 4 minus x to the exponent 4 all over h. And this is the limit as h approaches 0. Again, I'm going to use Pascal's triangle. So 1, 4, 6, 4, 1. Okay, we have x to the 4 plus 4x3h plus 6x2h2 plus 4xh cubed plus h to the 4 minus x to the 4 all over h. Okay, x4 minus x4, that's great. I'm going to factor out an h. We have x4 cubed plus 6x squared h plus 4xh squared plus h to the 3 all over the exponent 8, or sorry, all over h. Okay, those cancel. We can sub in h equals 0. That and that go to 0. What are we left with? We are left with 4x cubed. Okay, well, let's take a look at this pattern. For x squared, we get 2x. For x cubed, we get 3x. And x4, we get 4x. Now, we're going to take a look at these patterns and a quicker way of doing this through the remainder of this chapter. But just note these patterns.